Yes, hello, welcome back. The chapter of this video is actually optical images, lenses, lens rules. One important word here up front, it's not really embedded in the syllabus, so therefore this chapter will not be part of the exam. However, I still quickly wanted to summarize the rules for optical instruments, the lens rules. So, what is an optical device? Let's start with the most simple one, images and mirrors. So a real image would be, for example, the TV screen. A mirror is actually quite different. If this is your mirror, if you are standing in front of the mirror, what you see is, on the opposite side, your virtual image. What really happens is the light is reflected. You're not seeing the surface of the mirror directly, but the impression is you get a virtual image at the same distance, at the same size, on the other side of the mirror. So this will actually be also a chapter in lecture 2, second year, electrodynamics, virtual images behind a reflecting surface. That's what you really see. So that's what you should need to know. What happens if we bend the mirror? Spherical mirrors. So there are two options, a convex and a concave mirror. And in one case, if you have a parallel beam of light, each ray is reflected perpendicular to the surface, and what you get is an focal point F. So that's concave. And the other extreme case, convex. Again, the light is reflected perpendicular to the surface. And if you would now extend these lines, they would again all meet in one focal point. Reflection at the surface, and the result is all these light rays finally hit in that focal point. For the convex mirror, directly in front of the mirror. For the concave mirror, directly in front of the mirror. For the convex mirror, on a virtual point behind. This technique is also used to collect sunlight. Here, actually, sometimes they use elliptically curved lights, which has a technical advantage to collect light, especially on a certain point. So, spherical mirrors can be used also to magnify objects, but the much broader used technical instruments here are lenses. And I would like to add here, at the moment we treat a lens just as a thin lens. I will come to that problem in a moment. We are placing a lens into our beam. We have Snell's law. N1 sinus theta 1 is N2 sinus theta 2, and our index of refraction of glass N is between 1.46 and 1.52, depending on the type and quality of the glass. There's pure quartz glass. Glass can be boronated. There's lead glass, and each of them has a slightly different quality and therefore a slightly different index of refraction. This is actually widely used to later on, I'll discuss that later on, compensate for mistakes of lenses. So we have an incoming beam, let's say parallel. It hits a surface here. The normal is to the surface is shown here. So light then actually gets refracted inside and refracted a second time when it leaves the lens. The same happens actually on the lower part, and simply spoken for all these surfaces on the lens, and we get a focus here on the backside of the lens. This is a so-called convex lens. And now the opposite, a concave lens. And here the light is bent outwards. And if we would extend this line to the opposite direction, we would get a virtual focus on the opposite side. This is a concave lens. If we compare that with the mirrors, concave and convex, the concave reflecting mirror gave a real focal point, and the convex a virtual focal point. For lenses, this behavior is quite opposite. So the keywords convex and concave refer to the curvature of the surface and not to the final result, namely on which side the focus finally appears. So, this brings me actually to the lens rules. let me try to make a drawing here. Typical lens. And I would like to draw the focal points here, f and 2 times f on both sides of the lens. So if I place an object here between f and 2f, we'll get the following situation. One line, which actually is responding the beam of light, directly parallel to the axis, and one through the focal point on that side. Now let me extend that on the other side. And here, this one gets through the focal point here, and we can add a third line through the center of the lens. All the three will match on the other side, and you'll get a second object, a virtual image, on the other side. Now let's have a look. If you watch out carefully, you realize that the image, here our object, the lens, and the image the object was placed between f and 2f. The image now appears beyond 2f. That's the first observation. And the second observation is the size of the image is larger than the object. So we get a magnification here. So this can be summarized under the keyword lens rules. Let me just write it down first. F is the focal length. P stands for the object, and I for the image. So let me try to repeat this for an object which is placed the further distance than just 2f. F, 2f. F is the focal distance. So we place a larger object here now. One ray is just parallel to the optical axis, and here it passes through F. We get a second ray passing through F. Not quite, sorry for that. And here, from here onwards, parallel. And a third one just right through the center point. Sorry for that, I would really need a ruler for that. So now our image is located between f and 2f, and the size of the image is also reduced. So this already explains how you can use a lens as a magnification lens or to look up small images. Quick summary. What is if our object is close to the lens between f and the lens itself? So what is if p is smaller than f? In that case, we would not get an image at all. It would be divergent. What is if it's, no, that was correct, f and 2f? That was the first scenario. Here we get a magnification. If the object is directly at f, we would get an infinite spot. Other way around, if you have a parallel incoming beam, like from the sun, you get one sharp focus point here right in the middle. Think in your childhood you might have made that mistake or experiment at the beach. If you take a lens, then the sunlight is directly focused. If your object is directly at 2 times f, then actually the size of your image and the size of your object is equal. Object and image. Last but not least, if you place your object at a distance further away, larger than 2f, then you get a reduction in size. So this is the summary of the effects of a lens. And we interrupt here quickly. Just a quick interruption to clean the board. Let's continue. So I kept that image here for the magnification of an object. The object was placed between f and 2f. And even by just geometrical construction, you see that you get a magnification of the object, and the object appears at a distance now larger than 2f. The lens rule was as follows. 1 over f is 1 over p plus 1 over I. These are the distances for the focal point, the location of the object, and the location of your final image behind the lens. What about the magnification rate of the object itself? And that's parameter beta is the size of your image divided by the size of your object, and that's directly the distance of your image divided by the distance of your object from the lens. So P is the size of the object, and I is the size of the image. So these are the basic lens rules. And using that, and by combining 2 or 3 lenses, you can now build a telescope or a microscope. However, there are a couple of mistakes which we have to consider. I will not be able to address all of the corrections which are needed for a lens, but I will just highlight 2 of them. Typically, a lens is a finite object. So in the last drawing, I treated the lens as a plain, simple plate with no thickness. In real life, a lens has a certain thickness, and let me just draw that here in an extended version. We have a certain thickness. And if we now would draw our optical axis, the light travels here, and now a certain distance parallel, the same direction inside the glass body. And if we make a second line here in between, then you will see that this focal point for that ray would be at a different distance. So we get a spread of focus points. Way out is a so-called aspherical correction, where the surface of the lens is not cut perfectly round, but the shape, the curvature is corrected accordingly. A second very important mistake is the chromatic effect. If you look at the outer corners of your lens, the outer corner of your lens looks like a prism. And what have we learned already? For a prism, if we shine white light on a prism, we get a spread into the different colors, red and blue, and all the rainbow colors in between. The reason here again is that the index of refraction depends on the wavelength of light. Note again, n, the index of refraction, depends on the wavelength. So what you get in the end for such a lens, you get some color shadows in your image. There's a simple way out. You just use the central part of your lens that eliminates it partly, but the more professional way is achromatic lenses. And such an achromatic lens is simply built out of 2 types of glass. Let me just redo that again. Here we are using 2 two different types of glass. And now it's important that glass comes in different qualities. There are different kinds of glasses: borinated glass, lead glass, quartz glass, fused silica glass, BK7 glass, industry glass for windows, and so on. And the index of refraction is between 1.46 and 1.52. And now we can actually combine two glass bodies and glue them together with a perfectly calculated slope here, curvature of the boundary in between, and we can perfectly compensate for these chromatic effects. So the mistake created by the first lens is perfectly compensated by the other lens. So N1 is different to N2, and this is used to compensate both chromatic mistakes. The mistakes generated by the first lens is corrected and compensated by the second lens. So these are the fundamentals of lens rules. Now, without writing it on the board, I would actually quickly summarize what can we do now with these lenses, namely optical instruments. And first of all, let me please highlight some names. The fathers of optics. Famous name is Carl Zeiss. And you know the company name Zeiss. He was actually born in Leipzig and born in 1871 and died in 1924. Other important name, Ernst Abbe, 1840 to 1905 in Jena, or Schott, Otto Schott, still one of the most important producers of glass in the world, and perhaps you know the name Schott. Recently, a few decades ago, they invented the Ceran field, which is now used on an oven, on your oven, the glass plate there. So Otto Schott, 1851 to 1935, Jena. Another name, Ernst Leitz, Leitz microscopes or Leica cameras, 1846 to 1920 in Wetzlar, also Germany. So all these people were basically founding fathers of companies. I personally would call them businessmen in their brain, but scientists in their heart. So if they wouldn't have been founding fathers of companies, they would have become famous professors in optics, in physics, and we would call these lens rules now, for example, the Zeiss or Abbe rules. So these are the founding fathers behind. When the company Leica produced their microscope number 100,000, they awarded it to the last Nobel laureate in chemistry, and that was actually Robert Koch in 1906. So already in 1906, they had produced the microscope number 100,000. Side note, the Robert Koch Institute in Germany is now the core research lab for the coronavirus. Optical instruments. The first and most simple optical instrument is the magnification lens. We had discussed that here in great detail. The second important instrument is the photo objective, and that's basically just one simple lens, but of course corrected for aspherical and chromatic mistakes. The perhaps most important instrument is the human eye, And the capabilities of the human eye are remarkable and outstanding, and the calculation capacity behind the human eye is unbeatable. No modern computer would actually be able to compete with the human eye capabilities of the human eye. Well, the next two instruments are the telescope and the microscope. And perhaps I have time and patience and put that in a PowerPoint slide, but I think I'll stop that chapter here. Once again, optical instruments, lens rules are not part of the examination. I still thought that this is an important chapter for you. So thank you very much for your attention.